Uh, Good morning, colleagues, and good morning to the learners. My name is Amanda Sterman. I am going to present for us today technical sciences, and our topic is work, energy, and power. Work, energy, and power. So here we go. So learners, for our topic, we will start first with work. In our everyday language, the word work refers to the doing of chores. So when you say you are doing work, it means you are doing chores. But in the science language, work refers to something else. So I want us to deal with the science meaning of doing work. And as we do that, there are two words that we must keep in mind. The first one is going to be this word, force, which we learned in grade 9. And then the other one is going to be displacement. I believe in order for us to remember the definition and so forth, it's important for us to know the meaning of the words that are used in this definition. So for our science language, when we refer to work, we mean that there is a force involved and there is a displacement involved. Now, how are these involved? Let's start with the word force. Force refers to a pull or a push. So this we learned in grade 9, that a force is a pull or a push. And then displacement refers to the changing of position. Now, let's put the two together, force and displacement. It means that when there is either a pull or a push, and then the position of the object changes, then work is done. So if we have here on the surface an object, and then I'll start with a pull. There is a pull on the object, and then the object moves from here and it goes to another position. And if we check, the change in position is in the same direction as the force, then we can say work is done. If also we have a pull, because force is a push or a pull, let me pull this one at an angle. So here we are having a push, and here we are having a pull. So when there is a push or a pull and the object changes its position, then work is done. And now this brings us to the definition of work. If we look here, it reads that work is the product of the force applied on an object and the displacement in the direction of the force. So this explains that work, when we say we are working, it means there is a force that is applied on the object, and then the object changes position in the direction in which the force is acting. So from that definition, we have this formula for work. We say work is equals to F delta X cos theta. So from this definition, from this formula, The W is the work, the F is the force, and the X is the displacement. And then this part gives us the direction of the force. Gives us the direction of the force. So we must always remember that when we say work is done, we mean that there was a force that was acting on the object, and the position of the object changed, and it changed in the direction in which the force was acting. Now, let's note the following with regards to the direction. Now, if the motion of the object and the force are parallel to each other, so if motion and force are parallel, then theta is equals to 0 degrees. We said the force and the motion, the product of force and motion is what gives us work. So what we must note is that the motion in which the object is moving and the force, if they are parallel to each other, then theta is equals to 0 degrees. That's the first thing we must note. Then the second thing that we must note is that if motion and the force are anti-parallel. I just forget that symbol for anti-parallel, so I'll just write it in words. They are anti-parallel. Then theta will be equals to 180 degrees. Let's not forget this angle takes into consideration the direction of the force. And then the third thing that we must note is that if the motion and the force are perpendicular to each other, then this means that perpendicular, must gives us an angle of 90 degrees. Then we can say no work is done. So let's just recap a little bit. We are talking about work. The definition for work, I want to emphasize this, is that work is a product of the applied force on an object and the displacement in the direction of the force. Using the definition, let's see if we can state it using the formula. Work is a product. A product, we've got a multiplication sign here, and in maths terms we say that is a product. Is a product of the force and the displacement in the direction of the force. Now, what we must note is that first, the motion in which the object is moving and the force, if they are parallel to each other, then the angle theta, this is the angle in the formula, this angle will be equal to 0 degrees. The second thing that we must note is that if the motion in which the object is moving and the force are anti-parallel, to each other. Anti-parallel, that means they say the motion is in this direction and then the force is this way. Then the angle will be 80 degrees. Just to give maybe more clarity on this one, let's take the force of friction. This is the force that opposes the motion of the object. In other words, it acts in the direction opposite to the motion, and it's parallel. So motion is, let's say if motion is to the right, friction will be to the left. Therefore, that angle in between is 180 degrees. And then the third thing that you must note is that if the motion and the force are perpendicular to each other, in other words, they are giving us an angle of 90 degrees, therefore no work is done. Because if you use your calculator, you'll see that cos 90 degrees gives us 0. And anything that is multiplied by 0 is 0. All right. Then I want us to also understand that when work is done, then energy is transferred. So you must just remember that you've got work being done on the object. That means there will be energy that is transferred. I think we'll remember in grade 9 we said energy is the ability to do work. So we must just remember that. Now I want us to look at, I'm going to start with multiple choice questions so that we can see if we can give even a better meaning to what we've just explained. Let's look at 1.4. I am using the Technical Sciences Mechanics Summaries Terms Definitions of 2021. So if we look here, let's look at 1.4. 1.4, it says 2 men, X and Y, are pushing against a building. Y stops after 10 minutes, while X takes 5 minutes longer than Y. Which one of the following statements is true about the work done by X and Y? Now, when you are attempting to answer multiple choice questions, there are 2 strategies that I usually advise you must use. The first one is you must have the answer before you look at the options. That is, you read the statement, you understand it, and then you know what the answer is. That is just the recall from your understanding. Then you look at the option and you see, okay, the answer I have is one of the options. Then the second one is to use the elimination method. So for now, that means with the elimination method, you first take out the option that is incorrect, and then you deal with the one that is correct. So we said that in order for work to be done, the object must change position. Now here, as they are pushing on the wall, there is a push, so a force is involved. We've got a force, which is a push, so the force is there. And then there is no change in position. There's no change in position. The change in position is 0. Therefore, anything multiplied by 0 gives us 0. So we can say the work done will be equal to 0. And if we look at our option, is that since neither X nor Y are doing any work there. Why? Because the change in the position of the object where the force is being applied is 0. That was 1.4. So the correct option there will be A. And then the second one that I want us to look at is 1.8. Which one of the following statements on work is true? Work is done when, number A, the force is at 90 degrees with the direction of displacement. Let's try and argue why this one and see if this one is wrong. So the direction is 90 degrees. That means theta is equals to 90 degrees. And cos theta gives us 0. Cos theta, cos 90 degrees is equals to 0. I think even if we can use our calculator, because I know some of us, we are not very familiar with the use of our calculator. So you can see cos 90 degrees gives us 0. So if we go back to our formula, F delta x cos theta, and we just take these as they are, then we say cos 90. This portion is going to give us 0. And anything multiplied by 0 gives us 0. So this means that if the force is at 90 degrees, then no work is done. Yeah? Then let's look at the second statement. The displacement is in the direction of the force. If you apply a force on an object, let's go back to our definition. I think I'm just going to have to take my second booklet on the definitions page. If we go back to our definition, it says, and you look at the last part, it says the displacement in the direction of the force. So if a force is acting on the object, there will be displacement in the direction of the force. So this is a true statement. Let's just go further and argue the others. There is no resultant force and the displacement is 0. A resultant force is 0 and displacement is 0. So if no change, if this is 0, that means no work will be done. The option D, the displacement is 0 and the applied force is greater than 0. Even if the applied force is there, if there is no change in position, then the work done will be 0. So the correct answer there will be B. Now, multiple choice questions are very nice and interesting questions to practice if you want to test your understanding once you have studied, because you can use those questions to see just how well do I understand the work. And then the other question that I want us to look at is question 4. Question 4. Question 4 says, a man is pulling a toolbox of mass 60 kg across a rough horizontal surface using a rope. The tension on the rope is 300 newtons and is acting at an angle of 40 degrees with the horizontal. the toolbox is pulled over 3 meters. Now, when you are doing calculations with work, it's important for you to first make a schematic presentation of the scenario. But luckily in our question papers, most of the time we do have a diagram that explains what is happening. Then the second one is for you to draw a free body diagram. A free body diagram. Now, with the free body diagram, you have a dot. This dot is representing the object. And then we are going to draw lines. And then the lines must have arrows, and they must be in the direction in which the force is acting. Now, if we look at our object, it's resting on a surface. Therefore, the two obvious forces that you are having there will be the force of gravity and the normal force. Now, I usually say, if you are struggling to remember the symbols that are used when you are drawing a free body diagram, rather write it out in words. So this one would be normal force. So rather you write it in words instead of writing a wrong symbol and losing a mark. So rather you write it in words, then you get your mark. And this one would be gravitational force. Then when we look at this force, we are already told that they're using a rope, and then that is our tension force. And let me just, so this is T. I think we can also accept when you say it's the tension force. Then if we look in our statement, it says here, the object is moving across a rough horizontal surface. That means there is a frictional force that is involved. Now, frictional force, we know first, it's a force that opposes the motion of the object, and then secondly, it acts parallel to the surface. So here is our surface. So if this object is moving this way, that means if friction is opposing, friction will move this way. And it is parallel to the surface. I'm not very specific here with the length of my lines. Then you can write also here in words frictional force. So here is our free body diagram. Then you can already see that, okay, here are the forces that are involved. Then we go back to our definition of work, just for us to note. If the force and the motion make an angle of 90 degrees with each other, then no work is done. Then you can say, you just note for yourself, work done by gravity is 0. Why is it 0? Because the angle is equals to 90 degrees. Also, the work done by the normal force is 0. Why? The angle is 90 degrees. And you must do this in practice so that by the time you get to the exam, this is already in your system. Because you can imagine if you have to do this in the exam, it will take you a whole lot of time. Then we have a force here, tension force, and it is making an angle with the surface. From grade 11, we learned that whenever a force acts at an angle to the surface, then we have to resolve the force. We have to resolve the force. Now, if we look here, I hope my pink pen is very visible. We have the y component, sometimes called the vertical component of the force. And then we also have this component, which is the x component or horizontal component. So here is our force. It is acting at an angle with the surface. The moment a force acts at an angle, it tells you that you have to resolve. The simple term for resolve is just break down into its parts or component. Now, if I can just take you back to a little mathematics. In maths, we said that when we are dealing with a right-angled triangle, you know, most a triangle, the sum of the angles in a triangle is equals to 180 degrees. Now we are given this angle. I think it used to be like this. Then you will remember that this is the opposite side, and this is the, I'm still on the questionnaire, but I think I would just want to use this one question to somewhere do a little bit of revision from grade 11. This is adjacent, and this is hypotenuse. My spelling, excuse this last part of this word. So this is what we know from mathematics. Now, we use trigonometric ratios. I think we have sine theta being equals to opposite over hypotenuse. I'm not going to write this hypotenuse anymore. And then cos theta is equals to adjacent over hypotenuse. And then I'll just stick with this one. Now, for us in the science class, our opposite is the vertical component of the force, that is FV. And our adjacent is the horizontal component of the force. And then our hypotenuse is the force itself, sometimes applied force. So it's important that you know how to resolve. So I'm not going to even derive the formulas for you, but I'll just write it as it is. So to determine the vertical component, when you are given an angle and the hypotenuse side, you will use FV is equals to F sine theta. And then to determine the horizontal component, you will say F horizontal is equals to F cos theta. Right? So why am I doing this? It's to take us back to that definition of work, that in order for work to be done, the force and the displacement must be in the same direction. So if we're having a force acting at an angle, and we can see that, okay, when this force is acting at an angle, it has this vertical component and this horizontal component. That means that there is a component which is doing work and there is a component which is not doing work. Now, let's see. This horizontal component is parallel to the motion, and this vertical component is perpendicular to the motion. So if this one is perpendicular, that means the theta for the direction of work done, let me just write it here, from this formula, WF delta X cos, now I have too many thetas. Let's change this one into a beta. Let's make it a beta. Okay. Then this one will remain theta. So in this formula, that means work done by this force, which is in this direction of 90 degrees, is equals to 0. Work done by this vertical component, work done by the vertical component is in which the force is in which direction? 90 degrees to the motion. So the amount of work done by this force will be 0, which leaves us with the horizontal component. Now the horizontal component is parallel. Therefore, if it is parallel, that means theta in our formula, excuse my writing, it's all over the place now. Force, this is work done by the horizontal component, delta X cos theta. Now this theta is 0 degrees. That means the work done here is the work that is done by the horizontal component. And all of this you are getting just because you have interpreted the statement. And I think my teacher in high school used to say, a question that is half understood, I mean the question that is well understood is half answered. Now, you can even extend just on your own, maybe to say, here I'm going to have to calculate work done by frictional force, and I'll say friction delta X cos theta, and just remember my theta will be 180 degrees. And here I will have, let me just use a different color. Remember we said there is this component and then there is this component, and we are concerned with the horizontal component, and the work done by F horizontal will be F horizontal delta X cos theta, and just remember again theta here will be 0 degrees. This is your interpretation. Now, just remember this. I'm using this one to explain. When you are drawing a free body diagram, you are not allowed to show the force and its component in one diagram. I'm just using this to explain that when this is acting like this, as you are interpreting the question, you must note for yourself that there is a horizontal component, there is a vertical component, and the work done by the horizontal component, you will use this formula and you will note that, okay, it's in the same direction as the motion, therefore theta will be 0. And this one is anti-parallel, the force is anti-parallel to the motion, therefore theta will be 180 degrees. And then remember from our definition we said the force applied on the object in the direction of the object, and then there will also be displacement. And if you look here from this statement, there is a force and there is displacement. Ne? So work is being done, but not all the forces which are acting on this object are doing work. Now let's look at the first question. The first question says, define the term work done in words, in words, in words, in words. So when you define it, use the exam guideline, nothing else. I know we have many textbooks that we are using to study your study guides and so forth, but for your definitions, only state your definitions using the exam guideline. And the correct answer there is that work is the product of the applied force on an object and the displacement in the direction of the force. That is the only acceptable definition for work using the exam guideline. Then 4.1.2, calculate the net work done on the toolbox when it experiences a frictional force of 29.81 newtons. Net work done. Net work done. So let's see. I am quickly going to redraw our free body diagram. Now I'm gonna only include the forces which are doing work on the object. Forces, so that you don't get confused. Forces doing work. The forces doing work. Then we say we are given that this the frictional force is equals to 29.81 newtons. Frictional force is 29.81 newtons. There are many ways in which you can do calculations, whatever simple way works for me. I've found that for some learners who really struggle with this breaking down of formulas, when you use the free body diagram and you do the calculation there and you take it down, it takes time, but it works. So you start with the formula. Again, when you're writing a formula, use your data sheet, your formula sheet at the back. Our formula for work done is given there, that W is equals to the force delta X cos theta. Then you say, okay, if this is the magnitude of my frictional force, that means the work done by this frictional force is equals to the frictional force itself, the displacement, and the angle. Write the formula as it is. You get a mark for writing the formula as it is. Then you say my frictional force is 29.81 multiplied by my delta x is 3, and then I've got cos. Again, remember now we said this force is anti-parallel, therefore the angle theta is equals to 180 degrees. Then you take your calculator and you've got there 29,81 times 3 cos 108 is 89,43. You can verify 29,81 times 3 cos 180. We get the same answer. And our answer is 89,43. Now, we are dealing with work, and the unit of work is a joule. Now, remember that work is a scalar quantity. It's a scalar quantity, therefore, it does not have direction. Work does not have direction because it is a scalar quantity. So this negative sign, what does it tell us? It tells us that energy is being taken from the system into the environment. It's being lost by the system. But when we deal with energy, I'm going to explain further this negative sign. Then you come again here. You've got the horizontal component. When you calculate how much is this force, you will say is F cos, I'll use beta, ne? Beta will, because now I don't want to use too many thetas, is this angle between the force and the surface. And we say this is 300 cos, that angle is 40 degrees. And then we go 300 cos 40 degrees. And you can verify again 300 cos 40 degrees. Then you get 229,81 newtons. This is the magnitude of the force. It's the magnitude of the force, how big the force is. Then you can calculate the work that is being done by the force. The work that is being done, sorry for this untidy handwriting here. So the magnitude of the force is 229,81, and the position change of the object is 3 cos. Now again, this horizontal component is parallel to the motion, therefore our angle theta is 0 degrees. So you put 0 there. You already have the answer here in the calculator, so your answer multiplied by 3 cos 0 gives us it's 689,44 joules. Now, this is the information that you have, and the question is for 4 marks. Say, calculate the net work done. The net work done is the work done, is the sum of the work done by each of the forces. So you can say the net, the word net means sum of, that is you add things together. So it's the work done by the horizontal component plus the work done by the frictional force. Net work, sum of the work done. Sum, not sum like in language, sum like this. Sum plus Then we say, how much is the work done? Is 689.44 plus the magnitude. So this is the magnitude, 89.43. And then you take your calculator. Eight nine, 43. So the net work done is 600.01 joules. This step is what I call the needed type of process. That is, you make sure. Because I know some of us, if we use that long method with a long formula, we get it wrong. But let me do the other method as well. Where now, if you really now, when you are at that stage where you've got this, then you can just go ahead. And don't forget the subscripts. If you just write W, then W means nothing. It's work done by what? So it's important that you write your subscripts, because the subscripts, they tell us which of those forces is doing work. In this case, it's net work, and net work is the work done by the horizontal component and the work done by the frictional force. You can break down this formula and say the work done by the horizontal component is the horizontal component itself, delta x cos theta, plus the frictional, work done by frictional force is the frictional force, delta x cos theta. You can even break it down further to say the magnitude of the horizontal component is F cos, and then for that direction I'll say beta, delta x cos theta, plus, then you've got this one, you can keep as is because we know the frictional force, cos theta. And then we say, now you can just go and you substitute. We had 300 here, cos, we're given 40 degrees. You put this in the bracket. This is the magnitude of the force, and this is the displacement, and this is the direction in which the force is acting, 0 degrees. And then frictional force, the frictional force is 29.81, and the position is 3 cos, and then the direction cos 180 degrees, and you'll get the same answer. You get the same answer. So it's important, whichever way that gets you the marks, do that. Whilst you're still practicing and you still don't understand and you're not sure, if you can include all the forces all at once, then you do the step. You do the step. Now, I'm going to take the same question. I just want to change it a little bit. Let's say for this same question, this object of 60 kg with this applied force of 300 newtons at this 40 degrees angle. Now, if we were not given the magnitude of the frictional force and we still had to calculate the net work done. If we were not given frictional force, but we still had to calculate the net work done. Again, then I just want to make this dot bigger, and I'm gonna draw the components of the force. We've got here, we've got the gravitational force, we've got the normal force, and we've got the vertical component, and we've got the horizontal component, and we have the frictional force. So if we were given this same question, but instead of being given frictional force, like let's just go back to this question here. You see here they say it experiences a frictional force of 29,81. If this was not given, but instead we were given, let's say that the coefficient of the kinetic friction, let's say it's 0.15. The same question, then you must just remember that in grade 11, we looked at net forces. Now, when we are talking about net forces, we will have, let me say, F net horizontal, and we've got F net vertical. Vertical referring to up or down. Up or down, and horizontal being, let's say, right or left. So because you can get the same question, but now instead of being given friction, you are given the coefficient of kinetic friction. Now, first of all, you must know the magnitude of your forces. I think FV, okay, we did not calculate FV, but let's just quickly do it. If we look at, let's look at FV is equals to F sine theta, which is 300 sine 14, 300 sine 14. That gives us 192.84 newtons. And then FG is equals to mg. That would be, the mass is 60 times 9.8. And that will be 588 newtons. Then you have another force acting vertically, which is the normal force. Now, how do you determine the normal force? We go back to the definition of net force. Remember I said anything net refers to sum of. Once it says net, it refers to the sum of. So F net vertical will be equals to F vertical plus normal force plus the force of gravity, plus the force of gravity. Then we can say that from Newton's second law, the net force is equals to the mass of the object times its acceleration, Fv plus n plus Fg. Now, note here, there is no vertical movement. There is no vertical movement, which makes the acceleration to be 0. So m times 0. So acceleration vertical is equals to 0. This leaves you with Fv n plus Fg. So 0 equals to Fv plus n plus Fg. Now what you must note is that the net force vertically is equals to 0. Why? Because the objects are not accelerating vertically. Sometimes we have this misconception that when F net is equals to 0, then the forces acting on this object are 0, or they are non-existent. That is wrong. I'll repeat this. Sometimes we have this misconception that when F net is equal to 0, that means the forces acting on the object are 0. And I'm saying that is not correct. We can see here, F net is 0, but we are still having forces that are acting on the object, and the magnitude of these forces is not 0. It's greater than 0. The only reason F net is equals to 0 is because the acceleration vertical is 0. That means the sum of these forces together give you 0. And here you can just solve for I just made a small mistake here. Remember, forces are vectors and they have direction, and so if the upward direction is positive, then we take the downward direction to be negative. That means our force of gravity here is downwards. So we must include the direction for the force of gravity. And if we transpose that, we can have that Fg minus Fv equals to n. Then from this formula, you can go to your formula to calculate the frictional force. Remember I said if we take this same question, but now instead of being given friction, we are given the coefficient of kinetic friction, then what do we do? And I'm saying you calculate the normal force. How do you calculate the normal force? You determine first the other vertical forces. You can do it in one step. I was just explaining it step by step, but this can be done in one step using this formula. Forces are vectors, they have magnitude and they have direction. If you take up to be positive, down must be negative. So from this, vertical component is up, so we give it a positive sign. Normal force is up, so we give it a positive sign. Force of gravity is downwards, and we give it a negative sign. And you just here, you make n to be the subject of the formula. Then, once you have your normal force, you can calculate your normal force. How do we calculate normal force? We've got here vertical component, and we've got weight. Then we can use this formula. So from this formula, you can say this is the force of gravity minus the vertical component. And then you just go and say this is 0,15, this is 588 minus 192,84. And then you calculate your frictional force. Let's see. 588 minus 192,8. And minus 192,84 times 0.15. Then you'll get a frictional force. Like get 59,27. You calculate work done by frictional force, and you calculate your net work done. Now, in this instance, you can see that this is a pulling force. This is a pulling force, so the vertical component is upward. But now what happens if we have a pushing force? Same object, 60 kg. But now, instead of being pushed, remember we said a force is a push or a pull. So a force can push and a force can pull. So now, if this same force is now pushing, I'm just picking this from the top of my head. The coefficient of the kinetic friction is 0.15. Then what do you do? Again, it comes down to the issue of free body diagrams. The object and the forces acting on the object in their direction. Pushing force, that means you have a horizontal component, you have a vertical component. I'm using this type of free body diagram because I'm dealing with a calculation, and I found that when you use components to explain a calculation, it makes the work much easier. And you just have to make your dot to be big enough so that your lines are straight, they don't look skewed or something. And then friction again. Now, I want you to get into this habit of when you are drawing your free body diagram, some are define the forces. Some are defined, let's see. Frictional force, the force that opposes, you can see must there, here is our horizontal component going to the right. So frictional force going to the left. This one is going to the left, this one is going to the right. So frictional force is opposing the motion of the object. And it acts parallel to the surface. Then normal force, a force is exerted by the surface, which is in contact with the object, and it acts perpendicular to the surface or motion of the object. Gravitational force, that's our weight. Now, again, things to remember. This force, if you look here, it's making 90 degrees, no work done. This one, 90 degrees, no work done. This one, 90 degrees, no work done. This one, anti-parallel, angle 108. This one, parallel, angle 108. So just as you are drawing, get into that habit. Then you will see after 4, 5 practices, if you practice question, then it just comes natural that as you write, you just talk to yourself and you can see that things work together. Now again, our F net vertical will be the sum of the forces that are acting here. If we look here, we've got the vertical component. Sorry, I made a grievous mistake here. Grievous mistake. We are dealing now with a push, not a pull. Therefore, let me just scrap this and redo it. The vertical component will be downwards. The force is down. The horizontal component. The normal force. the frictional force and the force of gravity. Yes. Then the F net vertical is equals to the sum of all the forces that are acting. F net is N plus, now FV is down, is in the other direction now, so is minus plus FG. I write it this way because I want to emphasize the definition of net. Net is the sum plus sum of all the forces acting on the object. A force is a vector. It must have direction. So if up is positive, down will be negative. When you look at the free body diagram, normal force is up in the upward direction. You know, in maths, if we have a plus, you don't write it. Then plus vertical component in its direction, which is downwards, plus gravitational force in its direction, which is also downwards. Then from Newton's second law, which I think we all know that the net force acting on an object causes the object to accelerate. There is no vertical acceleration. Acceleration vertical is 0. So this part is 0. Then if we just bring this one down, and if we, let's just transpose. If we solve for n and we transpose, we are going to get Fg plus Fv equals to the normal force. Then you use this formula. Now normal force is equals to Fg plus Fv, and you know Fg is mg and Fv is f sine theta. So that is another scenario. Then the last scenario for this question would be if the force, let's take the same object, but now this force makes an angle of 0 degrees with the surface or with the horizontal. It makes an angle of 0 degrees with the horizontal. And again, you are given the coefficient of kinetic friction. Then if we look in our free body diagram, then we would have this applied force, we'll have this frictional force, we'll have this gravitational force, and we'll have the normal force. Then we can say, all right, again, to determine the normal force, I think this one we can see it directly here, but I'll still stick to just the same method. F net is, okay, this is F net vertical. F net vertically is equals to all the sum of the forces that are acting on this object. Again, a force is a vector quantity, so it has both magnitude and direction. So you've got normal force up, and you've got gravitational force down, which is indicated here. From Newton's second law, there is no vertical acceleration. This will give us 0, and therefore we've got n Fg. Therefore we can say Fg is equals to normal force. So those are the 3 scenarios. Now, I think I'm gonna deal with, again, I hope that question 4 was nicely expanded, but the section of energy will do it later. I just want to do another question on work. If we look at question, I think it's question 5. Question 5. Yes. A man applies, we're starting at 5.2. We're starting at 5.2. A man applies a force of 200 newtons to pull a crate full of bricks over a distance of 9 meters. The total mass of the crate with its contents is 120 kg. Define the work done. Again, when you define work done, you must use your exam guideline, which says it's the product of the applied force on an object and the displacement in the direction of the force. Now, you get your 2 marks. Then 5.2.2 says calculate the amount of work done by friction. This one is very specific. It's work done by friction. And we look here, we are given the magnitude of the frictional force. We are given the magnitude of the frictional force, and again we use our data sheet. We will find this for you. You will see the formula is like this. So what's important is that as you use the formula, you put in the subscripts which indicate which force we are talking about and the work that you're calculating, which force is doing that work. So I think it's 5.2.2. So our formula, we want the work done by frictional force, which will be equals to the frictional force times the displacement cos and theta. Remember, if the force is anti-parallel to the motion in which the object is moving, then your theta will be equals to 180 degrees. So the magnitude of the frictional force is given is 14 and the displacement is 9. Then this is cos 180 degrees. Write the formula as is. Don't substitute 180 degrees here. Write the formula as it is, and then in the step that follows, substitute. Then we've got 14 times 9 cos 118 degrees. Then you get a negative 360. We are calculating work, and the unit of work is a joule. Remember, work is a scalar quantity. That means it has no direction. That means it has magnitude only. Magnitude only. So this whole value, negative 360, is the magnitude. It's negative because it tells us that the system is losing energy into the environment. Now remember, when work is done, energy is transferred. I think we, let me see. Okay, let's finish this question, then we are going to take a short break. 5.2.3. What should be the size of the angle between the applied force and the direction of motion for the amount of work done on the crate and its contents to become 0? From this question, they are asking, what should be the size of the angle? What must be the size of the angle so that you can get the work being done to be 0. We know that when the force, if force and motion, if force and motion are at 90 degrees with each other, then the work done will be 0. So the correct answer there is 90 degrees. So the angle should be equals to 90 degrees. Then 5.2.4. Calculate the net work done on the crate and its contents. The net work done on the crate and its contents. A free body diagram is important again. The object is resting on a surface. That means the surface is exerting a force on the object because they are in contact, and this force is perpendicular. Then the weight, force with which the earth pulls object on its surface to its center. And then from here we can see that the frictional force is acting to the left, and we have an applied force of 200. Now this question is guiding you already, 5.2.3, that for work done to be 0, we said the angle between the force and the direction of motion must be 90 degrees. This implies that the normal force and the gravitational force are doing 0 work on the object. So the two forces are the ones that are doing work on the object. And then we write the formula. We want work net. This is 5.2.4. 5.2.4. Work net. I said net is sum of. Work net, sum of work done. So if it's sum of work done, sum of work done by the applied force, sum of work done by the frictional force. Work done by applied force is equal to the applied force itself, the change in the position, and the angle of the applied force, plus we already calculated work done by frictional force, so I think this one we can just leave it as work done by friction. Then we say the applied force has a magnitude of 200 times the change in position is 9 cos. This applied force is in the same direction as the motion, so the angle theta here will be 0 degrees plus the magnitude of the frictional force. Magnitude, I said work is a scalar quantity, so this is magnitude. This negative has nothing to do with direction, it's the magnitude. It just indicates that energy is being lost by the system. Then we have 200 times 9 cos 0. Cos 0 is 1. Then we've got 1,800. And a positive times a negative gives you a negative 360. 1,440. And the unit, make sure that whenever you write the answer, you include the unit. Let's take a 10 minutes break. 10 Yes, 10 minutes break. 10 minutes break, and then we will resume. Welcome back, everyone. Welcome back. We are now going to discuss energy. Remember, at the beginning, I said when work is done on an object, then energy will be transferred. In grade 9, we learned that energy is, it is the ability to do work. That's what we learned. And then just to give context for the purposes of our lesson, we are going to focus mainly on 2 types of energy. For us here today, we are going to look at 2 types or 2 forms of energy. We look at kinetic energy, and we look also at gravitational potential energy. So we said that when a force, just to go back a little bit, if a force is applied on an object, then the object must move in the direction of the force. And when that is happening, energy is being transferred. Now, an object, there are many other kinds of energies, which I'm not going to dwell on. So we're going to deal with these 2. Now, you must link this form of energy, link it with with motion. So when you are thinking kinetic energy, you must think motion. Motion means you must also think there is a velocity. If there is a velocity, from the definition of velocity, I think we have this. So when you think kinetic energy, you must tell you, oh, there is motion. There's motion, there is velocity. If there's velocity, there is a change in position over a given period of time. This brings us to the definition of kinetic energy. Now, according to our exam guideline, kinetic energy is the energy of an object due to its motion. The energy of an object due to its motion. So a moving object has kinetic energy. So you must know the definition. I'm not going to write it down because it's already here. The energy an object has due to its motion. Then the second thing is the formula. Formula is EK, sometimes they just use a capital letter K, is half mv squared. EK is equals to half mv squared. And then the symbols, you must know the meaning of these symbols. EK is kinetic energy. M is the mass of the object. And V is the velocity of the object. Now, the SI unit for velocity is meter per second squared. For mass, it is kilogram, and for kinetic energy is the joule. So, kinetic energy, the energy an object has because of its motion. Then the second form of energy. Now, when you are thinking of gravitational potential energy, you must think height. You must think height. Where is this object? You must think height. That means from the definition we can say that gravitational potential energy is the energy of an object due to its position above the surface of the earth. Above the surface of the earth. And then that's the definition. Then the formula is EP equals to mgh. EP is equals to mgh. Then from this formula, EP is the gravitational, sometimes just say potential energy, gravitational potential energy. So sometimes just loose to say potential energy, but must know it's gravitational potential energy. And again, m is the mass of the object, and h is the height of the object above the surface of the earth. The units, your height in meters, your mass in kilograms, and your energy in joules. Now, what must we note? Let's see. From kinetic energy. Okay, let's see this. From the formula of kinetic energy, we can see there you have a velocity. Now, if v is 0, then ek is 0. That's what you must note and remember. That's the first one. Then secondly, from the formula of potential energy, if H is 0, therefore EP will be 0, because H multiplied by G by M, anything multiplied by 0 gives you 0. 0 squared is 0. 0 multiplied by anything is 0. And then, so when a force is applied on an object, work is done. When work is done, energy is transferred. Now, for our purposes, for energy, we are going to deal with isolated system. Isolated system means that there is no external forces. There is no external forces. So there will only be two energies involved, which means the energy that is being transferred or when work is done is either kinetic energy or potential energy. Now, if we, let's say for example, if this is the ground and I have an object here on the ground, okay, let's say I'm standing there, is Memsterman, let me make a nice dress for myself. There is Memsterman holding a brick. I'm holding the brick in my hand. My hand is not moving, right? Now, from Newton's first law, we know that this object, which is in my hand, has the same velocity as my hand. So if my hand is not moving, it means the stone is not moving. It means the velocity is 0. So you will see words like at rest. The stone is at rest. If it is at rest in my hand, that means the velocity of the stone is 0. If the velocity is 0, it means the kinetic energy is 0. Ne? But the moment my hand moves, again from Newton's first law, the stone will be moving with my hand. So if my hand, so this was scenario 1, scenario 2, if my hand moves, that means now I throw this stone, then the velocity is not 0. So if the velocity is not 0, it means the kinetic energy of the object will also not be 0. Then this object is at a certain height above the ground. It's at a certain height above the ground, which means it is having with it gravitational potential energy, the energy an object has due to its height above the ground. So if H is not 0, that means we have potential energy. Now, this object, here's my stone, as it moves from this point to this point, let's say this is point A and this is point D. Between point A and point D, there will be a transfer of energy. I think we're familiar with the fact that energy cannot be created. You can't create energy, but it can just be transformed from one form to another form. So as the object is moving between A and D, the potential energy that it's having here, as it moves down, it's being transferred to the kinetic energy. And as it moves from this point there, the kinetic energy is being transferred to potential for energy and so forth. And if at this point it leaves with a certain velocity, that means it leaves with a certain kinetic energy. And all that kinetic energy, as it moves, it will have, because it is at a certain height above the ground, it will have both kinetic energy and potential energy. But if it was not moving, it will only have potential energy. Then the sum of the two energies, the sum, I think we've used this word sum a lot. The sum of this energy and this energy, the sum of these two energies gives us mechanical energy. The sum of the two energies gives us mechanical energy. The sum of kinetic energy and potential energy gives you mechanical energy. I think we have the definition here. Mechanical energy is the sum of the gravitational potential energy and the kinetic energy of a body. So, to calculate the mechanical energy, I'm used to this one. E mech is the sum of EK and EP. You can even break down this formula further to say EK is half mv squared and EP is mgh. Then, as the object is moving at any point, remember I said we are talking about an isolated system, meaning that there is no external forces acting on the system. And I think we might as well go to the definition of an isolated system, is that the net external forces acting on the system is 0. So as the object is moving between these 2 points, at any point, you will always have the sum. Let's say this is point, what's my other color? This is point B. You have the sum. At point C, you will still have the sum of the two energies. At any point, you have the sum of the two energies. At any point, the sum of these two energies, you will have it. Now, what we can say is that the sum of these two energies in an isolated system is conserved. It does not change. That means when you add them together, you get the same value always. That takes us to the principle of conservation of mechanical energy. It says that the total mechanical energy in an isolated system remains constant. The total, all of it, all of that mechanical energy were in an isolated system. Now, we said isolated system means the net external forces acting on the body is 0. There are no external forces. Constant means it does not change. Total means all of it. Mechanical energy means sum of kinetic energy and gravitational potential energy. Now, the formula is that EM initial is equals to EM final. Now, here, if we were talking maybe between points A and B, this will be your E mechanical at point A will be equals to the E mechanical at point B. And the E mechanical at point B will be equals to that one of point C. The one of point C is equals to that one of point. At any point, the total mechanical energy of this system is conserved. Then I think so that we can do the calculations for power and energy all at once. Let me summary do this. To say, let me just try and link this. We started here. Yeah, and we said when work is done, energy is transferred. When energy is transferred, the time taken to transfer that energy is power. So you do work. In order for you to do work, there must be a force and there must be a change in position. So when a force is applied on an object and the object changes position in the direction of the force, work will be done. When work is done, energy is transferred. Energy is transferred between two forms of energy. We've got kinetic energy and potential energy. And then this is when the system is in isolation. That means there are no external forces. And the time taken, you know, when the energy is being transferred, that happens over a period of time. Then we've got power. Power refers to the rate at which work is done. The rate at which work is done. I think if we look here, power is the rate at which work is done, or the rate at which energy is expanded. Then power has the symbol P, and it can be calculated using this formula. P is equal to W over T. If you look at this formula, W is the work done. So the time taken to do the work is what we call power, or the time taken to expand the energy is what we call power. And then we must just remember that the other formula to calculate power, if an object is moving at constant velocity, is that of Fv. Let's just remember that one. I think, yeah, everything else I will explain as I do the calculations. I'll start again with multiple choice questions. I'll start with multiple choice questions. Let's see. Let's look at 1.1.1.1. Let's look at 1.1. The graph below represents the relationship between work done on an object and the time taken. Work done and the time taken. The gradient of this graph, the gradient of the graph represents what? If we look at gradient, it's going to be work over time. Work over time. I said when we are doing a multiple choice question, one of the strategies is to have the answer before you look at the options, or to use the elimination method. In this case, I think if we look here, the gradient change your work over time gives you the power. So the correct answer there is A. And I think 1.3 was also the same question. Then 1.5. 1.5. A ball is dropped from rest from a height h above the ground. The gravitational force is the only force acting on the ball while it is falling towards the ground. Which one of the following quantities remains constant while the ball is falling? The first one, you have gravity as the only force. So that means the system is an isolated system. So the two energies that are involved is gravitational potential energy and kinetic energy. So when the object, let's say here is the object above and it is falling, it is at a certain height above the ground. As it is falling, the height changes. And from this formula, EP is equals to mgh. If height changes, EP will also change. So you can see that this one, gravitational potential energy, will not be constant. Secondly, as it is going down, the velocity is changing. Here they say it is dropped from rest. So it starts with a zero velocity. Then it starts to move. As it is going down, we can see that V is changing, is increasing. So from this formula, EK is equals to half mv squared. If this V changes, it means EK is changing. Therefore, kinetic energy is not constant. Then the third one, it started at 0. By the time it gets here, it will have a different velocity than it had here. That means velocity is not the option. So that is how you use the elimination method. You don't just say picky, 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 I eliminate, picky, picky, I eliminate, and picky, picky, whichever one my pens lands on, that's the one. It does not work like that. You must use scientific reasoning to eliminate the options, and you can only do that if you understand the work and you study. So that means the only quantity that remains constant here is the mechanical energy. And this takes us to the principle of conservation of mechanical energy, which says that in an isolated system. So if we look at this question and we look at the principle, I just want to do this. Okay. In an isolated system, here they say only force. That says only force is gravity. That means this is an isolated system. Total mechanical energy, sum of the kinetic and the gravitational potential energy, remains constant. Remains, which one is remaining constant? And when you go to the definition of mechanical energy, it says here, it is the sum of the gravitational potential energy and kinetic energy of a body. So that is how you use the elimination method when you answer multiple choice questions. And 1.6, let's look at 1.6. It says energy possessed by a body due to its position. Energy possessed by a body due to its position. I said when we think about potential energy, you must think position. That means it is your gravitational potential energy. Gravitational potential energy. And yeah, I think for our multiple choice questions we've done. So just try that. I think it would be good practice if when you study, after you are done studying, from however many question papers that we have, just deal with multiple choice questions. No long questions, nothing. Multiple choice questions. And as you look at the options, like for example, if we look at an option like a scenario like this one, this gives you an opportunity to define. So you've got 4 definitions: velocity, rate of change of position; kinetic energy, energy an object has due to its motion; mechanical energy, the sum of the potential and gravitational potential energy of the object; gravitational potential energy, energy an object has due to its position above the surface of the earth. Then you say, okay, this mechanical energy, when does it remain constant? In an isolated system. What is an isolated system? A system in which the net external forces acting on the object is 0. Is there a principle? Yes. What does the principle say? In an isolated system, total mechanical energy is constant. Just from doing one multiple choice question. So let's look at question 2. Question 2. Okay, I'll try to move a little bit faster. If we look at question 2, it says a 5 kg crate is at rest on a frictionless horizontal surface. The crate is then pushed by a constant force F of magnitude 10 newtons acting at an angle of 30 degrees to the horizontal. The crate moves a horizontal distance of 2.5 meters and reaches point B, the end of the horizontal and reaches point B, which is the end of the horizontal surface, at a speed of 2.94 meters per second. When the force is removed at point B, the crate falls a vertical distance of 0.44 meters to the ground. Ignore the effects of friction. I think just to avoid confusion, I'll do the whole of this question. Otherwise, I wanted to deal with question. I think I can still do that. There won't be any confusion. Let's see. So this force is acting on this object, and it pushes this object from this point to this point, and energy is transferred. When the object gets to this point, it has a velocity of 2.94 meters per second, and this point is 0.44 meters above the ground. I think we can do this question without necessarily going back. Then, because it says here, we only consider the motion from point B to the ground. From this point, that means it starts here with this velocity. So, if it has velocity, it has kinetic energy. And if it is at a certain height above the ground, it has potential energy. And the sum of these two at this point gives us the mechanical energy. And okay. Now, consider the motion from point B to the ground. It says, state the principle of conservation of mechanical energy in words. State the principle of conservation of mechanical energy in words. And it says, the total mechanical energy in an isolated system remains constant. The total, so the keywords, total mechanical energy, isolated system remains constant. That is how you state the principle. And then calculate the kinetic energy at point B. For you to calculate kinetic energy, let's see. Kinetic energy is EK. You must also have mass. You must have velocity. You must have that. So this one you want to calculate. The mass of the object is 5 kg. And at this point, the object has 2.94 meters per second velocity. Then, once you've written down what you are given, then you write there. The formula is 2.3.1. The formula, you take it straight as it is on your formula sheet. EK is equals to half mv squared. Half mv squared. We want to calculate EK. We have the half. And then the mass of the object is 5 and the velocity is 2.94. Do not forget to square. Do not forget to square. And then you take your calculator. Half is 0.5. So you've got, you can even put your calculator on the math mode. Then you know you've got 1/2. Then you've got 5. And you've got 2.94. And then you square that. And then you get, it is 21.6. You must round off to 2 decimal places. So when you are rounding off, it means we want 2 decimal places. So you must check the number that follows. If it is 5 and above, then we are going to add 1 here. So this will be 21.61. We are dealing with energy, and the unit is a joule. Right. And then 2.3.2. 3.3. Calculate the gravitational potential energy of the crate at point B. Gravitational potential energy, we want to calculate. Let's use a different pen. EP, I'm loving this pen of mine. M and H. Then you say, I want to calculate EP. Do I have mass? Yes, it's 5 kg. Do I have H? Let's see. Do I have H? 0.44. Is it in the correct units? Yes, it's in meters. 0.44 meters. Then you go to your formula sheet. I think I must just try. I've been talking about formula sheet, and I've not actually shown what is a formula sheet. This is a formula sheet. It's written data for technical sciences, grade 12 at the top. Then you are having the constants, the physical constants. Then you'll see on this data sheet, table 2, you've got forces. All the formulas that go here, you have. Then you've got work, energy, and power. That means the formulas that we are going to use are these ones. You must just try to familiarize yourself with these formulas. You look at them and you say, okay, this one, gravitational potential energy. This one, work done. This one, kinetic energy. This one, power. This one, power. This one, mechanical energy. And you can see mechanical energy is the sum of the kinetic energy and the potential energy. I've been talking about data sheet, formula sheet, and I've never actually shown you one. So in case you've never seen one, this is a formula sheet. On your question paper, it will be right at the back of the question paper. So you can take it out and place it in front of you when you are writing, so that you are sure. And whenever you're doing homework and classwork, make sure it's in front of you so that you know that you must use it. All right, so we want to calculate EP. Let's see here. EP here. Sometimes you can use U. I'm so used to using EP, so I'm not going to change. I will stick to using EP. So EP is equals to mgh. And g in this formula is the gravitational acceleration or acceleration due to gravity. It is a constant. The value is 9.8 meters per second squared. And then you substitute. EP is equals to, you've got 5 times 9.8 times 0.44. EP, and then on your calculator you've got 5 times 9.8 times 0.44, and it gives us 21.56 joules. We are dealing with energy, so the unit is a joule. Then 2.3.4 says use the principle of conservation of mechanical energy to calculate the speed at which the crate hits the ground. So the crate is going to move from this point to this point. Now, the formula for our principle, unfortunately, is not given. You can see it's not here, it's not here, it's not here. That means you must remember it. You must remember it. But what does it say? It says the mechanical energy, EM initial, is equals to EM final. So we are having 2 points. Remember I said mechanical energy at any point will remain constant. So the object is moving from this point with a velocity and is coming to point D. So we must have EM at A and EM at B. I'm so used to EMAC. I must fix myself. EM at A and EM at B. Remember, at this point, the mechanical energy is the sum of the two energy. And also at this point, it is the sum of these two energies. You can even break down to say it is half mv squared and mgh. Also here, half mv squared and mgh. It will just depend what it is that you are given. And in the previous questions, we calculated a kinetic energy at A. We also calculated a potential and gravitational potential energy at A. Then when it hits the ground, let's note that the height is going to be 0. The height will going to be 0. That means here at the ground, the potential energy is 0. But it's hitting with a certain velocity. So this velocity is not 0. What we can do is to say, okay, at A, we have EK, we have EP. Then at B, or final, EK, I think here because we want velocity, we can say at B. For EK, we are having the mass and we want the velocity. Then for EP, H is equals to 0, so EP will be 0. Then the velocity is what you want to calculate. The mass of that object has not changed. Here you've got EP 21,56 and EK 21,61. This is what you have. I hope it's not confusing. This is at A and this is at point B. So it moves from here to hit the ground. So this is A and this is B. We already calculated EP and EK. And here EP is equals to 0 simply because H is equals to 0. And we want to know the velocity. So we write our formula. Say E M initial or at A is equals to EM final. So the initial simply is where it started and the final it's where it ends. So here we've got EK plus EP and here we've got EK plus EP. Now this one we've got, so I'm just going to retain this side of the formula as it is, and we want to calculate this side, the velocity. So there's no need to break down everything, just keep as it is. The EK is 21,61 plus EP is 21,56 equals to half times 5 v squared plus 0. And you simplify. If we simplify, we start with this side. I think it's even better if we just say 5 divided by 2. And we say, let's have, okay, let me not confuse you. We'll say 21,61 plus 21,56. That gives us 43,17. We multiply by 2 and we divide by 5. Then we get 17,268. But we are not looking for v squared. We are looking for v. So we are going to take the square root of the answer and we get 4,1. Now we must round off to 2 decimal places. So if we look at this number, it is 5. So we are going to add 1 here. It's going to be 6. And then the units for velocity is meters per second. Meters per second. I'm going to try and find a question that also has power. I think it was question 6 that I wanted to do. Question 6. You see, as I'm discussing these questions, I'm only taking them bit by bit, so that each question addresses what I am talking about. So if we look at question 6, it says a worker dropped a spanner from a building of a certain height. When the spanner reached a height of 17 meters above the ground, the velocity was 3 meters per second. The mass of the spanner was 0.5 kg. Assume all the effects of friction are negligible. Assume all the effects of friction are negligible. So from here, you can see that the spanner is dropped and then it goes to a certain height above the ground where the velocity is 3 meters per second. The mass is 0.15. Ignore friction, which means you are having an isolated system. Then 6.1.1. 6.1.1 says, define the term mechanical energy. Mechanical energy, again, I said, when we define, we must use our exam guideline. We must use our exam guideline. So let's go back to our exam guideline. It says mechanical energy is the sum of gravitational potential energy and kinetic energy of a body. The sum of, and the questions, the way that they are arranged, the one that precedes the next question gives you an idea of what you need to calculate or use. Because if they say define mechanical energy, and when we look at the next question says calculate the mechanical energy. So if you know what mechanical energy is, you will be able to calculate mechanical energy. So when we are defining, we referred to these words, sum of. We said sum of kinetic energy and potential energy, and sum of is sum of. So the sum of these two gives us mechanical energy. So it's very important that we remember that definition. The sum of the gravitational potential energy and the kinetic energy of a body. The sum of. Then 6.1.2. Calculate the mechanical energy of the spanner 17 meters above the ground. So the height at which this object is above the ground is 17 meters. That means if this is the ground and the object is here, then the object is at 17 meters above the ground. And at this height, it is having a velocity of 3 meters per second. So if you make for yourself this schematic presentation, then it gives you an idea of what is happening. Then you can see that let me go back. You want to use calculate EM. This is what you want to calculate. So in order to calculate EM, you must have kinetic energy at that point. And kinetic energy, you will need in that formula mass. You're going to use mass, and you're also going to need the velocity. And you also need, for the potential energy, you are going to need again mass and height. So you want to find the mechanical energy. The mass of this object is given. It's 0.15. So you say mass is 0.15. Again, here you've got 0.15. The velocity is 3 and the height is 17. Then you've got all the values that you need. Then you go to your formula. The formula is EK plus EP. Then you can just break it down to say this is half mv squared plus mgh. And then you have half. It's important to substitute correctly. Half times 0.15, and we've got v squared. Do not forget to square, plus 0.15 times g is a constant and it is given on the table, and the height is 17. And then you just type everything in there, on the calculator. We've got here 1/2 times 0.15 times 3 squared plus 0.15 times 9.8 times 17. And our answer and our answer is 25.67. 25.676.12. 6.12. Remember, when we are rounding off, we check the state number. It's 5 and above, we add a 1 here. So it's 25.67. And again, we're dealing with energy. So the unit is joules. That was 6.12. And 6.13, it says, calculate the velocity of the spanner after it had fallen 11 meters below the 17 meter height. If we look here, at this height, it is 17 meters. So if it goes from this point 11, let's say it is here, and this is 11 below where it started. So for us to get 17, it means it is at 6 meters above the ground. So it is 11 it is 11 meters below that 17 meter height. That means it has covered 11 meters. So at this point, it is 6 meters above the ground. Just get a full page. So we want to know the velocity at that height. So remember, this is 6.1.3. Our definition, EMAC, I'll just say initial, is equals to EMAC final. We already have EMAC initial. We just calculated EMAC initial. But we want the velocity at this point. So the velocity is going to be the sum of the mechanical energy final will be the sum of the kinetic energy plus the gravitational potential energy. And we already have this one. So when we substitute, I already showed you that the height here is 6, and we want to know the velocity. The mass of the object has not changed. Then we've got 25,67, and we substitute half times 0,15. We want the velocity plus 0,15 times 9,8. Now it is at a different height of 6 meters above the ground. And if you simplify that, you are going to get that your V is equals to 14,99 meters per second. Start here, you transpose, multiply by 2, divide by 1, 0,15, and you take the square root. Then 6.1.4, calculate the velocity with which the spanner hits the ground. Calculate the velocity with which the spanner hits the ground. So now they are saying the spanner, let me use blue, it's hitting the ground. When it's hitting the ground, that means H is going to be 0. Therefore, EP on the ground will be 0. So we will say this is 6.1.4. We have EMAC initially, and now our EMAC final. Now this we have and EP is 0 plus half mv squared. Sometimes you see we just break down the side of the formula that you need to calculate a variable from. So we have EMAC stays the same, doesn't matter where the object is. My mic has just fixed it. It doesn't matter where the object is. Your EMAC stays the same, and in this case our EMAC is 25,67. And I already explained that on the ground, when the object has reached the ground, then the height is 0. That means EP will be 0. Then half times the mass of the object did not change, and we just calculate the velocity. And you'll see that the velocity is going to be, if we say 0,5 times 0,15, and then we say 25,67 divided by the answer, and we take the square root of the answer, then we are going to get that the velocity is 18,50, and must not forget the unit is meters per second. Then when it comes to power, there's a new unit that we have not used, horsepower. This horsepower, I wish I could draw a nice horse, but if this is a horse, there's my horse, and just give it eyes. So horsepower, 1 horsepower. This is the power. In the olden days, before this sophisticated language, they needed to give context by referencing to something. So horses, they pull carts all the time. So if this horse, let's say we have tied to it a bucket or a bricks and so forth, yeah? So the power, that means the rate at which energy is being used by this horse, we say it's 1 horsepower. And they said, okay, after many experiments, they say, okay, if I use 1 horsepower, it's the same as when I have 746 watts. If there is 2 horses, I'm not going to draw the second horse just in case I scare people away. If there's 2 horses, then there's 2 horsepowers. That means there will be twice the amount of power in watts. 10 horses, 10 horsepowers, 10 times the amount of power in watts. That's how we do the conversion. So it's important for you to know how to convert. I just wanted us to maybe understand better this horsepower. Now, a worker applies a force of 60 newtons to lift a toolbox from the floor to a height of 0.5 meters in 1.2 seconds. Assume that 1 horsepower is equals to 746 watts. Which formula can be used to calculate horsepower when the object moves at constant velocity? Let's see. From this, we are having a force of 60 newtons. We are having a time of 1.2 seconds. We are also having a displacement of 0.5. So which formula can we use? Now, if we go to our formula sheet, just get the formula sheet. If you go to our formula sheet, we've got the formulas with work, and we've got one with a force. Now, from this one, velocity, you remember we said velocity is equals to change in position over time. So if you have position like you have here, and you have time, and this is constant velocity, that means you do have velocity. Therefore, to calculate power, this formula would be the most relevant formula to use. So 6.2.1 will give us the formula P is equals to FV. P is equals to FV. Then calculate the power of the work. Express the worker's power in horsepower. I like this horsepower because it just makes me to imagine how many horses are there. 1 horsepower, 1 horse, 2 horsepower, 2 horses. Okay. 6.2.2. So, and it's important, power, when they say calculate power, they are also saying calculate the rate at which the work is done. They are also saying calculate the rate at which the energy is being transferred. So your mind must tell you that, okay, power, there is energy transferred, there is work being done, there is change in position, there is a force, and motion of this object is in the same direction as the force. So with all these variables that we have, we can say, okay, we can start by calculating here velocity, and we say this is 0.5 over 1.2, which gives us 0.5 divided by 1.2. It gives us 0.42 meters per second. This is not our final answer. We just keep the original answer in the calculator so that we can reuse it. FV, the force was given is 16 times the velocity is 0.42. Therefore, the answer multiplied by 60 will give us 25 watts. Now, they said we must express the answer in horsepower. So 1 horsepower gives you 746 watts. That means 25 watts will give us X number of so just cross multiply this, you'll have 746. This unit and this unit will cancel out, times X equals to 1 times 25. Then you divide by 746 on both sides. This and this gives you 1, so you have X. And therefore, that means you have 25 divided by 746, which gives us 0.034 horse powers. That means you've got, hey, the size of the horse is so small. It's not even 1 horse, ne? 0.034 horsepower. So the size of the power that you have is that of if you had a very tall horse, let's say. We've got how much time? 15 minutes. I think I should just use this time to wrap up what I have been saying all along. Wrap up what I have been saying and just see if I can make a story. So we've got a force, which is a pull or a push. It is changing the position of the object, ne? So these two, they give us the work done, and then that means you must remember so if there is a push or a pull and a change in motion, there will be work done in the object. Then the formula is this. Then if this force is parallel to motion, theta is 0. If the force is, let me say, I'll use this one for lack of remembrance of this sign that I wanted to remember. So this is motion and this is force. If they are like this, therefore theta will be 180 degrees. If force is going up and motion is this way, can you see? They make a nice angle of 90 degrees. And theta is 90 degrees. Then you can say no work is done. No work is done. Then we also said if work is done, then energy is transferred. If work is done, energy is transferred. Now, what you must note is that we are dealing with an isolated system. What this means is that there are no external forces. There are no external forces. Therefore, you must consider two forms of energy. Yeah? First one is kinetic energy, and the second one is gravitational potential. Energy. Yeah? Now, kinetic energy, as the formula EK is half mv squared, and we must think motion. For kinetic energy, you must think motion, and gravitational potential energy is EP is mgh, and you must think here, you must think height, and then the two kinetic energy and potential energy, they give you the mechanical energy. And when the system is isolated, this one is conserved. Mechanical energy is conserved, which means, this implies that at any point, the mechanical energy at this point will be equals to the mechanical energy at that point, because it is conserved. And then you can break down this formula. So if the system is not isolated, that means if there are external forces, then you cannot use the principle of conservation of mechanical energy. And to state this principle is, we refer to our exam guideline, and we say that in an isolated system, the total mechanical energy is constant or is conserved, or we can say the total mechanical energy in an isolated system is conserved. Now, when energy is transferred, that means it will take a certain amount of time. Yeah? So with time, we always say rate. When you see rate, you must know the time or period over which something is happening. So the rate at which this energy is being transferred refers to power. It is power. Power is the rate at which energy is transferred, and we see this from the formulas that are used. Rate at which work is done. Rate at which energy is transferred. And if the object is moving at constant velocity, then P is Fv. Remember with this V that velocity by definition is change in position over time. Rate of change of position. So if and then I think the last thing is that power, the SI unit is a watt. After I think it's James Watt or something. Watt. Yeah? Now, the amount of power generated by one horse, I don't know how big this horse has to be. I'll try to find out. But I think it must be a very big horse, not a small horse. So, 1 horsepower will give us 746 watts of energy. Yeah? Which is, I think if we divide this further, 746 divided by 1,000, see, 746 divided by 1,000, it will give us a kilowatt. Kilowatt. Now, just since I still have time, I want to say that I know we've just discussed work, energy, and power, but even in other topics as well, when you study, read through and then give meaning to the words that you are reading. The words must mean something. This assists you to remember the definitions. Don't just cram the definitions, but know what they mean. Know what the law means. If you are given a principle, know what it means. Like this one that we've just discussed, that in an isolated system, the total mechanical energy is conserved. Know what an isolated system is. Know what the word total means. Know what the word constant or conserved means. If you do that, then you start to understand the work and the practical applications of the work that you are studying. And also, the other thing, use multiple choice questions. I know we love these long questions, but if you really want to understand the work, start with the multiple choice questions. Go through the multiple choice questions, because I think I did show earlier on how you can use just one multiple choice question to basically go through half of the work that you are dealing with. So good luck for 2021. Do well and just do your best. I think what do I want to say? There is something I want to just share quickly. I hope I can find this. That it's from a book that is titled The Secret. Basically, on this book, it says your thoughts are like a magnet. Whatever you think about, then that is what comes to you. And I think this one is, if I can read, okay, it's from a quotation from Lisa Nichols. It says, when you focus on lack and scarcity and what you don't have, you fuss about it with your family, you discuss it with your friends, you tell your children that you don't have enough, or you tell your friends that you don't have enough, or you tell your friends that I don't think I can do this. We don't have enough of that, we can't afford that, then you'll never be able to afford it, because you begin to attract more of what you don't have. If you want abundance, if you want prosperity, then focus on abundance, focus on prosperity. So I think even this is what I'm using for myself, that we want our learners to pass. Our learners want to pass. That is exactly what we should focus on, because that is exactly what we are going to attract. We want them to do well. That is what we should focus on, them doing well. Then that is exactly what will happen, because our thoughts, our words, and our actions are going to be directed towards doing well and them doing better. Thank you, and all the best for 2021.